Hello and welcome back to Calculus 1, section 2.5, limits at infinity. That's the enthusiasm. So, the previous lecture was infinite limits, where answer was supposed to be infinity. Now, limits at infinity, input is infinity. So, we are looking at the problems which have limit x goes to plus or minus infinity, which could produce the finite number or infinite number or does not exist, right? Can produce any of those answers. So the difference between the sections, right, 2, 4, and 2, 5, the difference is where this infinity is. Is it the answer or the input? So now we are talking at limit at infinity. So we want to see what is happening as we let our independent variable grow indefinitely. So we go back and we consider our function 1 over x. We also realize that limits give us the y value. And when we draw the graph, we can consider the question limit of 1 over x as x goes to positive infinity. Positive infinity is this way on x-axis. So what is the y value approaching as the x goes to positive infinity? It's approaching 0. There is a really cool paradox called Zeno's paradox that is thousands of years old, where philosopher Zeno said that when you throw an object or shoot an arrow, right, the object will cover half of the path with another half remaining, and then in that half will cover half with another half remaining, and then in the remaining half will cover half with another half remaining. And if you rinse and repeat forever, how is it possible that arrow strikes the target or that the object actually hits? And in our terms, how is it possible that you are actually sitting in those chairs where technically you are always covering the other half of the trip that remained? So if I am to draw this paradox with let's say an arrow, so we have a target there, right? And you have the guy, let's make him a little bit fatter. There we go. Some neck there. We need the hat with the, obviously. There we go. It's going to be a bow, and the hand that holds that, and then the arrow. There we go, with the other hand that holds that. That was fine. Now, when you shoot this thing, right, hits the target, the distance it travels from here to here is the, let's put him on a straight ground rather than the incline. Then you have to do some physics as well. It's still on the incline. And we'll have the levitating target. It's okay.
I feel like a certain calling was missed for you.
We can make it better. All right. So that's too much. So what's happening here? Somewhere is the halfway, and the halfway remains. But then there is a half of that half, which we know it's a quarter. And then there is a half of that half, which is an eighth, and the half of that half, which is a 16th, and so on. Zeno's paradox states that if you always have a half of the remaining path left to cover, you should never reach destination, whether it's you or the arrow or the object. Yet I know that if I am to toss this at you, you're going to move, because you know what's going to happen if you don't move. Why does the arrow hit the target? See, the concept of the limit came about 2,500 years after Zeno. So he couldn't understand and explain the paradox, which was paradox at that time. Today it's just a perfect little math problem that we do in the margin of the book. If you model the remaining path, and that path is, in this case, 1 over 2 to the n, or 2 to the x, whatever, x, where x counts how many halves you have left, right? And you send that x to infinity because you say, you know what, it should never end. What happens with the remaining path when you divide 1 to infinity? It goes to, yes, it becomes a 0, which is the reason why the target was struck by arrow, or why you are sitting in the chair that you are sitting. See, the idea of division by infinity is easily understood because every time you divide by a number, the result is smaller, right? Hollywood cashes in on that, right? Because they can always get the movie going with the 5 guys that rob the bank and then they start killing each other, right? And that's a movie. So the concept there is very simple, right? The less people share the cut, the more of the cut there is, right? So the idea is that the more people are sharing one thing, right, the less they get. Which is why it's dangerous when you go to a party to let the civilians, you know, dig into pizza and all that stuff, and you kind of wait for civilians to clear and then you go. No, you go clear it out and then let the others. So now what's happening here is this is the limit at infinity. We all know that this function graphs as a decay function, and we also see it from the graph that the function will, right? This is where 1 is, and the function will eventually, not eventually, in infinity, it will be 0. What concepts can we deduce from such calculation? Well, we have 2 concepts that we consider. One is the concept of horizontal asymptote, and the other one is the concept of end behavior of the function. Again, both of those are discussed in your pre-calculus, and we are going to now add the rigorous definition, right? And we're going to perform the limit rather than the whatever voodoo we perform there in pre-calc. So where do we begin? First, I would like to work out an example which illustrates those rules which you memorized for horizontal asymptotes. If you remember, what you did is you only did horizontal asymptotes, you only considered horizontal asymptotes for polynomial functions because you were asked to memorize the 3 rules when exponents are the same, when top is bigger, when bottom is bigger, right? And then that means the asymptote does not exist, or it's 0, or front coefficients, and so on. Well, you don't need to know that anymore because now we are going to define through the limit, and you just take the limit. which is something that you should know because welcome to Calc 1, right? So all of those rules that you earlier memorized, now you don't need to know anymore. Say that you have a problem which states that the limit as x goes to infinity is x squared plus 3x minus 1 divided by 2x squared minus 8. No, minus 7. There we go. Does anyone remember what would be the horizontal asymptote for this function from PreCalc 1? Yes. Yes, 1/2. Very good. The exponents are the same, and because the leading exponents are the same, that means that the front coefficients will give us the asymptote, and that asymptote is at 1/2. Nice. But let's say you don't know that. So how do we solve this limit? When you have polynomial divided by polynomial, divide each of the terms with the highest exponent that you have, x raised to the highest exponent that you have in the entire problem. In this case, it's x squared, so I will divide 5 times by x squared. When we simplify, we get 1 plus 3 over x minus 1 over x squared divided by 2 minus 7 over x squared. Remember what I wrote before? Limit of any number divided by x to any exponent is equal to 0 as long as x goes to infinity. The limit of any number divided by x to any power as x goes to infinity is 0. So every single one of these will go to 0. And you are left with 1/2, which turns out to be asymptote at y equals 1/2. When you face the problems with polynomials, division of polynomials, you can divide by the highest exponent term everywhere. So you can have, let's say, x cubed and everything else to be x squared and below, you would divide by x cubed. If you have 2x to the 5, you divide by x to the 5. So you always divide by the highest exponent, even if it's repeated in the problem. So now it's time for us to talk about horizontal asymptote. If the limit of x goes to positive or negative infinity of f of x is a finite value L, then f of x has a horizontal asymptote at y equals L. This is the only statement you need to know because it transforms the issue of horizontal asymptote into a limit problem of Calculus 1. You don't care whether the function is the square root function or radical, rational, polynomial, exponential, trigonometric. You don't care what that function is because, and you don't have to learn case by case. You know now that you can take the limit of that function. If you get the finite value, you have horizontal asymptote at that value. So now you go back and you say, okay, 1 over x. So you put 1 over x there. The limit of 1 over x as x goes to infinity is what? 0. So horizontal asymptote at 0. Again, make sure that you write the equation y equals 0, not h equals 0. That makes no sense. Let's consider the function f of x equals x cubed minus x plus 1 divided by x squared minus 1. Yes. Infinity. Do we have horizontal asymptotes? Yes or no? No? Why not? Yes. You need the sunglasses now. Give her the sunglasses. We do not have horizontal asymptote in this case because the limit will not be finite. But we are reminded that we are going to have a slant asymptote because we have a situation where the numerator exponent is by 1 larger than the denominator exponent, which is the condition for slant asymptote. It only happens when you have polynomials divided, and this is that case. So we employ our limit, x goes to infinity, to try and solve this. So x cubed divided by x cubed minus x divided by x cubed plus 1 divided by x cubed, and x squared divided by x cubed minus 1 divided by x cubed. You see that you get 1 over 0. Not finite, therefore no ha. The definition clearly states if the limit is finite, that limit is the asymptote. Well, in our case, the limit was infinity, was not a finite value, therefore no horizontal asymptote. However, we do have slant asymptote. Depending on whose textbook you used in the past, it might be called the oblique asymptote. That's another way, oblique asymptote. So we do have a slant asymptote, which we compute using long division of polynomials. So I will divide x squared minus 1 into x cubed minus x plus 1. X squared goes into x cubed x times. Multiply back, we get x cubed minus x, right? When we subtract that, they all cancel, and then we have the 1, and then x doesn't go into 1, so we're technically done. Slant asymptote at y equals x. This function here will always be a linear function, y equal mx plus b, because when you divide the degrees that are 1 apart, right, you always get the first degree back as the answer. I divided a cube by a square, and then when you go 3 minus 2, it's 1. So that's the condition. The condition states that the degree in the numerator has to be by 1 larger than the degree in the denominator. And the reason is, when you subtract, the difference of them is 1, which provides you with the slant asymptote, which is the linear equation. And that's that part. There is a remainder here. We could have, gone and said plus 1 over x squared minus square squared minus 1, but we don't care about it because we are not going to add that to our asymptote. So far, you know how to find vertical asymptotes by using the one-sided limits. You know how to find horizontal asymptote using this trick of dividing by the highest exponent. And then slant asymptote, which occurs only when you divide two polynomials and only when they are by 1 off, right? Numerator is 1 degree higher than the denominator. So that's what we know so far. But then we also know that there's end behavior of functions. And that's simply considering this chart. If this is x, this is y, and you have a behavior of a function that goes like this, I hope that you can in your head disassemble this motion into two motions like this. So clearly, every problem that lives in this quadrant would be a problem where the limit of f of x as x goes to positive infinity is positive infinity. Because as x goes to positive infinity, the y shoots up to positive infinity. And now you can draw the same thing in other three quadrants. I mean, similar. So this behavior, which can be decomposed into these, is the limit of f of x where x goes to negative infinity and we're getting positive infinity. We have the other two. So quickly, limit x goes to negative infinity of f of x produces negative infinity because the y goes down forever. And limit x goes to positive infinity of f of x gives you negative infinity again. It falls down. This is called the end behavior of functions. So it can, the end behavior, right, is when it goes to one of these infinities, or it's hitting the asymptotes, right? Or it just ends abruptly, like square root of x, right? Square root of x starts at 0 and then goes along. So now, why is this important? Because of the analysis of functions. Eventually, as I said, we use differential equations to write mathematical models, and then we use the limit to check the validity of those models. And I'll give you an example of that. But first, let's do a cut and dry math problem where we examine, let's say, e to the negative x. So analyze y equal e to the negative x. Well, you know how to graph it. Looks like this, going through 1. And what you can do quickly is you can say limit as x goes to negative infinity of e to the negative x gives us positive infinity. And we see that that's the end behavior. End behavior is that as the x goes forever to the left, y will forever rise, which is the reason why I said negative infinity. There we go, much better. So as the limit of x goes to negative infinity, we see that the function e to the negative x goes to infinity. Now, limit as x goes to positive infinity of e to the negative x, we are getting 0, because now we're talking about this situation. You go all the way to the right, and that all the way to the right is positive infinity. I mean, sorry, 0. Yeah. Limit at infinity. Try to consider those titles and words that are used and how they're used. Limit at infinity. Does the limit care what's happening here? Absolutely no. Limit at infinity only considers what happens with a function at infinity. End behavior of the function considers what's happening at the end of the function. So both of these concepts are only considering the very ends of the function, leaving the middle portion of the function completely detached to horizontal asymptotes and end behavior. Implication of this is that the horizontal asymptote can be pierced. And we are going to see that in chapter 4. Depending on how involved the problems were in 2.6, if you took PreCalc1 at RVCC, you might have seen problems where you know there is a horizontal asymptote at 0, and then all of a sudden the function goes through it. And it might explode your brains, right? Because you think of these asymptotes as impenetrable walls. Well, they are walls for vertical asymptotes. Vertical asymptotes cannot be pierced under any circumstances. Vertical asymptote is impenetrable wall. But horizontal asymptote, you can pierce through it, because that asymptote doesn't care what's happening locally. Because of that situation, you have a problem whose graph is going to look like this. Now, this is chapter 4, but the discussion remains in this section. You computed 2 vertical asymptotes, and you also computed the horizontal asymptote in red. So you know that you have 3 asymptotes in this problem. And let's say the configuration of the graph looks like this. You have this, and you have this. And then in the middle, that. Over here, the function pierced through horizontal asymptote. And that is okay. Functions can also pierce through slant asymptotes as well. None of these concepts that we study in 2.5 are localized. They are powerful and must be obeyed at infinities. So, these 2 parts here are governing the horizontal asymptote. And you cannot cross horizontal asymptote at infinity. Locally, you can. And we are going to use this piece of information in chapter 4, section 3, when we graph functions by hand. So remember this concept, so you don't have issues on second guessing yourself on the exam, saying that, oh, I can't cross the asymptote. Vertical asymptote cannot be crossed, horizontal asymptote can, and slant asymptote can. Out of all places I could have clicked on the computer, I clicked and X'd out my examples. So now we understand how horizontal asymptote works, and that the horizontal asymptote are obeyed at infinities. The problem that I wanted to share in terms of application and why is important. So we had the electricity example, right, for a vertical asymptote and buildup of infinite energy over time, which is the actual experiment we can do. The less violent but far more scary, in my opinion, problem would be the population, right? If you solve differential equation which says that the change in population is proportional to population, you employ separation of variables, integration, and all of the other cool stuff that you guys are going to learn in calculus, you come up with the population model which says that population in time is equal to initial population e to the kt. Now, whenever you solve a problem in differential equation, you get a function as an answer, and that function is supposed to model something in our world, whether it's biology, engineering, economics, whatever, medical field. The first thing that you should do when you have a model is to see how that model behaves if you let it run for infinite time. And our variable here is time, so I'm going to take the limit of p0 e to the kt as t goes to infinity. What is the answer? What do we get? What do we get? Infinity. Now, is this a viable population problem for, let's say, humans or rabbits on the Earth for a long run? Hell no. If you know that the planet is a ball, well, close approximation of that, and because it's a 3D ball, it has the finite surface area. Can you fit infinite amount of people on a finite surface area? Now that we have a global warming, which means the water is claiming the ground, and then also deserts are expanding. Actually, from year to year, we have less space unless we figure out and how to live on water, underwater, deserts, and so on. So you see that this population model is not good for describing the population on the long run, because there's no way that you can fit infinite population on a finite surface. So that prompts us to look for a different model that would be a better fit. Again, you look at the limit for that model, and then you, as you send time to infinity, and then you look into that one and say, okay, so that one is better, and then right, so and so. So there's a logistic model which would have mathematical constant called carrying capacity, which is what our planet has. Now scientists can decide if that is 10 billion or 12 or 15, because that depends on calculations of the on approximating the average energy consumption and food consumption and everything else. But it's important to understand that this graph here looks like this, with the end behavior being positive infinity, which we see right in our limit. And then if you consider the logistics growth, You start with the initial population P0. This is your P0 for this problem. That population grows exponentially, and then it levels off because it's hitting that carrying capacity K. Carrying capacity is going to be the maximum amount of people or rabbits or bacteria that planet can sustain. Any more than that, we are running into issues of negotiations for food and energy, and we know how we negotiate, right, amongst ourselves as a primitive species we are. So the trick is, when you are considering mathematical models, no matter what they are, taking the limit and sending the limit to infinity is actually very beneficial, because you see how your model is doing on the long run. Again, as engineers, most of this stuff is worked out for you in textbooks and reference materials and so on. So you look up the stuff and you quickly compute what you need. But if you're a researcher or working in a more advanced environment like NASA and NSA and SpaceX and so on, where people are pushing the frontier, well, you have to be able to detect these things and correct in your models for that, so the design that you're working on actually works. So that's that part. I wanted to see if we can find a few more examples to calculate. What do we have? Another 3 hours, so we're good. They're just here. Oh, before I go any further, this thing pops up over and over, and I'll do it in blood. So the inverse tangent graph looks like this, and it's bounded by negative pi over 2 and pi over 2. The function f of x is inverse tangent of x, and when we actually have two horizontal asymptotes, so the limit as x goes to negative infinity of inverse tangent of x is negative pi over 2, which is this thing over here, and then you have the limit x goes to positive infinity of inverse tangent of x, which is giving you positive pi over 2. This graph pops up, the limit of this pops up over and over the calculus courses and differential equations. So deal with that now. Those are the horizontal asymptotes. Can you have more than two horizontal asymptotes? You think so? One, two. It's cut and dry. It's really evil stuff. No one's feelings are considered. Can we have more than two horizontal asymptotes? If you look at this particular graph, this one is obeyed at infinity, which means this end of the function can't go anywhere else. This one is also obeyed at infinity, which means this end of the function can't go anywhere else. These two horizontal asymptotes fully consume the entire function. So is there a way to actually have another infinity involved? The answer is no. Still, because you can't. See, the trick is that you will lose the function if you put another horizontal asymptote to be followed. Because at that point you will have function on top of the function which fails vertical line test, and it's done. So you can have one or two or infinitely many vertical asymptotes because they partition domain, and function can be stretched in between them, and that's fine. You can have at most two horizontal asymptotes. To have a third one, that means that you would have another piece of the function going to either positive or negative infinity, which is going to be on top of already existing piece, right? And that would not work. So you can have 0, 1, or 2 horizontal asymptotes if you are considering functions, and no more than 2. Vertical asymptotes, you can have any number of them. You can create an example with 500 vertical asymptotes. You know that tangent, let's say, has infinitely many vertical asymptotes. So that's something that, you know, that kind of analysis needs to be there. Now, they do have some spicy examples here, so let's take a look at those. These problems are awesome. Problem 41. It says 4x cubed limit as x goes to infinity of 4x cubed plus 1 divided by 2x cubed plus square root of 16x to the 6th plus 1. We are not going to rationalize here. Okay? We cannot solve it by plugging in infinity, because all you would get is infinity divided by infinity. And at some point in chapter 4, you will see how when you divide two infinities, you can get 0, or you can get 1/2, or you can get infinity. So all bets are off, depends on the function. So how would you do this problem? The answer is you would do it the same way as your polynomial problems. You would divide by the highest exponent in the problem. Now, what is the highest exponent that we actually have there? Yes? It's a 3. What's the square root of x to the 6th? X cubed. You see? So all of them are actually x cubed. If you divide by x cubed, these are clear. When you divide by the x cubed on the outside of the root, when that x cubed undergoes the square root, it becomes x to the 6th. Cancels here and divides there. So let's go divide each one of these guys by x cubed. Move that x cubed into the radical to become x to the 6th. And then cancel a whole bunch of stuff. Let's see how it works. Everyone finds it. I've never heard in the last 7 years the student would say that whatever book we use, Stuart, Thomas, and now Briggs. I've never heard a student say that Boston is harder or not able to understand it. They always say that, which is the reason why it's interesting. Are we all agreeing on 2/3? Well, every time you divide 1 by infinity, you get 0. So it dies. Right? This is the part where you divide 1 by infinity, it goes to 0. You divide 1 by infinity, it goes to 0. So both of these go to 0 because it's a number divided by infinity. Again, for those of you who are figuring out this 1 divided by infinity piece, when I take this 1, this is 1 piece of paper. When I take 1 and divide it by 2, the answer that I get, there we go, the answer that I get is a piece which is smaller. I get 1/2. 1 divided by 2 is 1/2. 1 divided by 4 is 1/4. So now you see that my denominator went up, but the size of the paper got smaller. The result, right? So this is the result when you take the paper and you divide one paper. You take one paper and you divide it by 4, you get a smaller answer. So this is 1 divided by 1, and this is 1 divided by 4. Now, if I divide by 8, right, that's by 8, divided by 16, I have 16 of these in here. 1, 2, 3, 4, right? So 16 of these. And then you keep dividing the 32, 64, 128, 256, right? 512. So as you can see, the denominator going to 512, I can barely hold the answer. The answer that started from 1 and then 1 over 512. So it makes sense when you extend this, when you divide 1 by infinity, your 1, magic, right, is 0. So 1 divided by x, or 1 divided by x squared, 1 divided by x cubed, or 6, all of them in infinity go to 0, leaving only numbers around. So this is our calculation for this section. Anytime you see that, they go away. Make sense? Of course, it's math. Of course it makes sense. Right?
So one of the most important things to remember is that when you have x to a number power in the denominator, it's going to go to infinity, which would mean 0.
Yes, it kills it. Yep. There is another notion that we will eventually see in our class where this is true for functions that grow faster. You know that exponential function grows faster than polynomial function. So if you divide polynomial function with exponential, exponential grows faster and the whole thing is 0 again. Because when you divide slower rate with the bigger rate, right, faster rate, it acts as 1 over x or something, and it goes to 0. So we'll deal with that as well. Actually, let me just make sure that it's not here. It's not. Slant asymptotes, one more time, occur only when you are dividing polynomials. So if you have sines and cosines and e to the x's and logs and stuff, don't worry about slant asymptotes. You only worry slant asymptote if it's a polynomial divided by a polynomial where the degree in the numerator is by 1 higher than the degree in the denominator. And that's the end of the story. Cool. Let's see if they have some other nice problem for you to enjoy. All right, so let's now work on problems that you are going to see on homework somewhere. Again, it's end behavior. Anytime they say end behavior, you can translate that into analyze. You analyze graphs for stock functions, for stock market, for graphs that you need in a lab, and so on. So graph analysis is important. So let's see. I'm interested in two graphs. 47, f of x equals 1 minus ln x. And then we'll do 48 absolute of ln x. You guys didn't tell me that is the stream okay? Yeah. Because my okay, whatever. Okay, thank you. Because on my end it doesn't look good. Yeah, it's. I just tried refreshing it, but it. Anyway. right. So for the analysis of the graph, you had enough time, hopefully, to finish both. So for the analysis of the graph, I would first like to rewrite the first one as negative ln x plus 1. I see that this plus 1 over here is going to be shift up, and this negative here is the reflection. On which axis? X-axis or Y-axis? X-axis. So to graph this by hand, I'm going to reflect and then take this point and shift it up, so the graph actually looks like this. So the original graph, gray, is like this, is just ln x, and this is negative ln x plus 1. Actually, I can write 1 minus ln x. And behavior. We see a vertical asymptote at 0. We see that the limit as x goes to 0 from the right, plus, of our function 1 minus ln x in parentheses is positive infinity, which means vertical asymptote at x equals 0. We also see that the limit as x goes to positive infinity of our function 1 minus ln x is negative infinity, which is the end behavior. Function is decreasing, has no min max, right? That's all other stuff that we will eventually add to this list. But now we were considering asymptotes, we were considering these things. Now, the next part is the absolute x. And I believe I talked about this, right, the first day. Exactly this function. What are we going to do for this? How do you graph absolute of ln x? Like this? Up, yes. So the original function should look like this, right? But then we are not allowed to have a negative piece. That negative piece needs to be above because of the absolute value. And I lost the ability to draw, which means we should be done. I still can't draw. Let's say this is perfect.
This is perfect.
Thank you. This is at 1. So looking at this, again, limit x approaches 0 plus from the right of our function absolute x is equal to positive infinity. Therefore, vertical asymptote at x equals 0. And end behavior limit x goes to positive infinity of absolute value of ln x is equal to positive infinity. So we have the end behavior, which is as the function goes to the right, it goes up. It will have a minimum point at 1, 0. It's decreasing, then increasing, or concavity and other things that we will discover in chapter 4. We are just doing the this first analysis, which is end behavior. One more problem and call it a day. Two more problems and call it a day. Yes. Does it have horizontal? Right? Does it have a horizontal asymptote? Nope. It does not. Horizontal asymptote at 1 would look like this. And you can see that neither end of the function follows that line. Horizontal line at 1 goes through y equals 1, parallel to x-axis. We don't see function hugging that line on any of these ends. In order for it to be a horizontal asymptote, function has to hug it somewhere, positive or negative end.
Could it be a negative one?
No, because we show that at the end behavior, we are getting, as it goes to positive infinity, it goes to negative infinity, so it's not going to hang around negative 1. We stop drawing at this point here. That doesn't mean that there is an asymptote somewhere below, because end behavior prohibits that. End behavior says that this will go to negative infinity, which is forever down, and in infinity, vertical asymptote is the finite number, not negative infinity. So the two concepts are in opposition. Therefore, it's impossible to have. You can't have the end behavior show infinity and horizontal asymptote at the same time, because horizontal asymptote, by definition, is the finite value and the end behavior is infinity. And those are not the same concepts in any circumstances. So that's why no, we can't have on any negative number just because we computed that. All right, let's see what you guys are not going to like. So, horizontal asymptote of f of x equal to, lock the doors, square root of x squared plus 2x plus 6 minus 3 outside of the root divided by x minus 1.
That's what people strive for. Right? It always needs to be. I don't just retire and do nothing and have money. That's one power that I wish. Whether we should not work and not do anything.
And the horizontal asymptote is 1. Nice. How do we find horizontal asymptotes? We solve limit x goes to infinity. That is definition. You learn that, you use it. Finally, you're understanding that calculus is about learning theorems. Theorems tell you how to do the problem. This theorem in red states that if you take the limit as x goes to positive or negative infinity and you get a finite value, that's your horizontal asymptote. There's nothing else that you need to know. Obviously, you know how to take the limit, but that's not the matter of this section. That's the matter of previous sections. So you build up. So question says, where's the horizontal asymptote? I learned that the way to find horizontal asymptote is to find the limit. X goes to infinity. What do I divide by? What do I divide by so that we can do this? Divide by x. Highest exponent is x. When it undergoes the square root, becomes x squared. So now it's x squared over x squared plus 2x over x squared plus 6 over x squared minus 3 over x divided by 1 minus 1 over x. We simplify everything. Square root of 1 plus 2 over x plus 6 over x squared minus 3 over x, 1 minus 1 over x. One over 1, and we get 1. Horizontal asymptote is at 1. If we have horizontal asymptote, can we have slant at the same time? No. They are mutually exclusive. It's one or the other, never both. You can have neither, right? e to the x. The ln x doesn't have horizontal or slant. It's fine. Polynomial function doesn't have either one of those, right? So we're good. Do we have a vertical asymptote here? Do we have a vertical asymptote here? The correct response at this moment in time is maybe. because you see that the candidate is where? At 1. But without doing the limit, you don't know. You have to do limit x goes to 1 to show whether there is or is not limit there. Great. All right. So that's it for this section. I'm going to end this.